In this lecture, we're focusing on integrals that have trig functions in them. Before I do anything else, let me recall some identities that you're supposed to know. So if you can remember, the sum of angle formulas for cosine. So if I have cosine of alpha plus beta, the formula goes cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. So let me change that then to cosine of 2x, and you can think of that as cosine of x plus x. And so x is both the alpha and the beta in this situation. So you get cosine x minus sine of x, sine of x. And that'll equal cosine squared of x minus sine squared of x. Of course, I can replace sine squared of x with 1 minus cosine squared of x. And we'll end up with 2 cosine squared of x minus 1. Now, what I want to do, let me bring this cosine of 2x down. I'm going to solve for cosine squared of x. So I'm going to add 1 and divide by 2 to get the following. And you can do similar things with sine. You would have, let's go back, cosine of 2x was equal to cosine squared of x minus sine squared of x. I can, instead of swapping the sine squared, in place of cosine squared, I could put 1 minus sine squared of x minus sine squared of x. And so I get 1 minus 2 sine squared of x. If I solve that for sine, so there's a couple of things here. I would subtract 1 and then divide by negative 2. I get sine squared of x equals 1 minus cosine 2x over 2. So whenever we encounter sine and cosine to the second power, this is the way we'll go to integrate them. For example, suppose I want to integrate sine squared of x dx. Well, I will rewrite it like I just have it there. And what I'll do is I'll bring the 1/2 out front. It really doesn't do much for us there. And so we get 1/2 x minus, remember here, if you do a u substitution on 2x, du will be 2 dx, but you'll divide by that 2. So what happens is you'll get minus, let me put the 1/2 out there and then I'll distribute in a minute. Then I'll get minus 1/2 sine of 2x. Now we get plus c. And then I'll go ahead. You can multiply through by 1/2 if you want. It really doesn't matter. This finishes off the problem. All right, this time integrate. We have sine of 2x times cosine of x dx. Now, since you have a 2x and an x, you can't let u be sine and du be cosine. And you could go and back your way up, I suppose, and try to get something from that. But you should recall another identity. That sine of 2x equals 2 sine of x cosine of x. So this integral becomes 2 sine of x cosine squared of x dx. That's because I took this cosine of x and multiplied it to that one. Now I can let u equal cosine of x. Du will equal negative sine of x dx. Or better yet, let me put the negative in front of the du and change that to a positive sign. So this becomes negative 2, the integral, u squared du, because I've got the negative taken care of, and then I need sine of x dx, and there's sine of x, and there's dx. So that equals negative 2/3 u to the third plus c, and then let me put my u back, which was cosine. So remember 2/3 cosine to the third x plus c. For the next example, we'll try sine squared of x cosine squared of x dx. Let me fix that too. And I'll use the formulas that I had before on both of them at the same time. So sine squared was 1 minus cosine of 2x all over 2, and cosine was 1 plus cosine of 2x all over 2. Now what I'm going to do is I'll bring this 2 and this 2 out front to bring me a 1/4 in the out front. When you multiply these two things, it's a difference of squares. So you're going to get 1 squared minus cosine squared of 2x dx. Of course, the square on the 1 is not a big deal, so I'll get rid of that. Now, I have a square, so I'm going to apply the formula again. So the formula for this was 1 plus cosine. Now, it's going to be 4x over 2, because you multiply by 2 whatever was inside of here. So 2 times the 2x gave me the 4x. Let's see, this is 1/4 the integral from, well, there's no limits, 1 minus 1/2 minus cosine of 4x divided by 2. I'll simplify here. 1 minus 1/2 will be 1/2. I like to do this. It helps me a little bit with integration. Then when I take the antiderivative of cosine, I'm going to get sine of 4x over 4. Of course, this one right here will become 1/2 x. And then here will become minus 1/8 cosine of 4x plus c. For our next one, we're going to do cosine cubed of 20x dx. So the natural thing to do here is to break this up into cosine squared of 20x times cosine of 20x dx. And then I'll use the major, the most used of all the identities. That's the one that says sine squared plus cosine squared equals 1. To rewrite the first part as 1 minus sine squared of 20x times cosine of 20x dx. And now I could let u equal sine, so I could do u equals sine of 20x, and then du equals cosine of 20x times 20 dx. So I'll divide the du by 20. And this integral then becomes, I'll put the 1 over 20 out here, 1 minus, this will be u squared. And all of this over the 20 will be the du. So you get 1 over 20 times u minus 1/3 u cubed plus c. And then u, where to go with sine of 20x? So I end up with 1/20 sine of 20x minus 1/3 sine cubed of 20x plus c. For this next one, we'll have sine cubed of x cosine to the fifth of x dx. Now, there's more than one way to do these. Your book probably will do it a different way than I'm going to do it. But what I'll do, I have something in mind, and I'll explain hopefully while I'm doing it. I'm going to take the even powers of sine and cosine and strip them away. So I'm going to have sine squared of x, and then I'm going to have cosine to the fourth of x, and then what's left over will be sine of x cosine of x dx. Next, I'm going to run those identities through. So I'm going to do the one for sine. That's the 1 minus sine of 1 minus cosine of 2x all over 2. And then I'm going to have, this is like cosine squared times cosine squared, so I'm going to get 1 plus cosine of 2x over 2. There's one of them. 1 plus cosine of 2x over 2. There's another one. And then I have sine of x cosine of x dx. Well, let me start multiplying stuff out. 3 2's I'm going to bring in the front to make a 1/8. And let me start by multiplying this times this. It's a difference of squares, so that's nice. I get 1 minus cosine squared of 2x. All right, now I'll go ahead and FOIL this all out and see what happens. So I'll get 1, that's 1 times 1. Then I'll get plus cosine of 2x. And then I'll get minus cosine squared of 2x. And then finally I'll get minus cosine cubed of 2x. And all of this is times sine of x cosine of x dx. And I don't like a mixture of 2x's and x's. So what I'm going to do is remember that sine of 2x equals 2 times this. So what I'm going to do is right here, I'm going to put a 2 in front of that sign, but I'm going to change this out here to a 16. That way I can use the identity for sine of 2x. This piece right here is sine of 2x. So I have 1 plus cosine of 2x minus cosine squared of 2x minus cosine cubed of 2x times sine of 2x dx. And now I have a nice u du thing that I can use. If I let u be cosine of 2x, du will be negative sine of 2x times 2. So let's do that. U equals cosine of 2x. Du equals negative sine of 2x times 2. Remember the chain rule. So what I'll have there then is I'll have negative du over 2 equals sine of 2x dx. So let me block this off so not to be confused with the rest of the problem. So this becomes, let me see, a negative du over 2. So I'm going to have negative 1 over 32. And then I'm going to have 1. There's a u plus u minus u squared minus u cubed du. That part there in conjunction with the negative 1/2 is the du. So I'll end up, now just integrating those u's is simple. This has become a polynomial. I'll have u plus 1/2 u squared minus 1/3 u cubed minus 1/4 u to the 4th Don't forget your plus c. And then what was my u? U was cosine of 2x. So let's throw those in there. Negative 1 over 32. We have cosine of 2x plus 1/2 cosine squared of 2x minus 1/3 cosine cubed of 2x minus 1/4 cosine to the 4th of 2x plus a constant. All right, now I want to show you something that can help you quite a bit in your work. Let me go into my web browser, start it up, and in the top, in the address bar, type www.integrals, and you'll be confronted with the Wolfram Alpha page. If you've ever heard of Mathematica, Wolfram is the company that makes it. So it will allow me to check. I can just type it in just like that, and I'll hit enter and see what she does. So, wow, it looks like they got a common denominator. Let's check theirs against mine. Well, I'll tell you what, I'm going to, it shows you that the right thing is in there. So let me go ahead and copy this picture. All right, let's see. Now, mine would have had negative 1 over 32 cosine of 2x. Is 72 divided by 3072 equal to 32? Then the next one, I'd have had negative 1 over 64. Is this 1 over 64? And the next one, I would have had positive 1 over 96. Notice though, look at this stuff. They have gone and made these all into things like this, and there's mine. So what do I do about something like this? What do I do as far as checking when their answer is so much different than my answer? Well, as arduous as it may sound, a good idea is to graph. See, the idea is this. Two integrals are considered the same if they differ by a constant. So go to your y equals, and now as arduous as this may look, I'm going to put my negative, and then I don't think I'll have to put the negative 1 divided by 32 like this because it's horizontally oriented, or it won't let you do multi-lines. And then let me go ahead and throw in the rest of the stuff. I'm going to have cosine 2x, finish it off. Then I'm going to have plus, I'll have cosine squared of 2x over 2. So what would I do there? Cosine of 2x. Now I'd like to square that. Oh, well, that's nice. Squared, it puts it up in the exponent, so then I can divide by 2 and it's not so bad. Move it out of the way so I can get the rest of the stuff. Then I have negative 1/3 cosine cubed of 2x, so I can go negative cosine 2x to the third and divide by 3. And the last one, we're going to minus cosine of 2x, cosine 2x to the fourth, and that was over 4. And don't forget to finish off the parentheses. So I'll hit enter there. Now the problem that Wolfram gives me, the version they give me, has a 3072 plus a constant. That's what they use. So let me see if I can put this in. I'm going to put the 1 over 3072 first. So I'm going to do 1 divided by 3072. And now let me put the rest of the stuff here. So I got negative 72 cosine 2x and I have minus 12 cosine of 4x. And I have plus 8 cosine of 6x. And then finally, plus 3 cosine of 8x. Now, if you go and do a zoom 6, I'm not sure what this is going to tell us just by looking at these two things. Quit. Oh, let's go. You can do go to. Let's find the go to error. It doesn't like what I did here. Probably, when you see a small thing like that, what I did is I hit that button instead of the full minus. So let's try again and see if I get an error. Boy, oh boy, look at that. It's very useful. And if you do trace, will tell you how big that you're dealing with. Oh, well, no wonder. We're dealing with very small numbers here. All right, fine. So let me go into the window and at least change the y values to something very small so I can see what I'm doing here. From -1 to 1, and let's see if I can get a look at this thing. Well, I see stuff. If you hit on, it'll stop the process. And let me go and change my window to even smaller. Let me go from -0.1 to 0.1. And then graph it again. See what happens. Ah, there we go. It's slow. This is the first curve, by the way. That would be, this one is my answer. Now let's take a look. Theirs is coming now. They're close, but I'm not so sure they're exactly the same. So one way I can find out if they differ by a constant. Let me stop this. This is not helping, even though they look like they could be close to the same. What I'm going to do for my last thing here then is in y3, I am going to graph y2 minus y1. So you go to vars, y vars, enter, enter, enter. Now, if you go up here into the equals, I don't care about their graphs anymore. I'm gonna, if you hit enter, it'll put an unblock on it, and that way it won't graph. So the only thing that will graph here is y2 minus y1. Let's take a look at the graph. And I'm going to stop it and make the window even smaller. I'm going to make this, the y max, into 0.05, half the size, so that I can take a look at it. Oops. One last thing, the window down here. It's above the x-axis, so I'm going to do 0. What do you call this? This would be the graph of a constant. That means that my answer and the answer of Wolfram are both correct because these two things differ by a constant. If you need more information to indicate to you that they do differ by a constant, go to the table and take a look. y3 was where I did y2 minus y1. Look at these numbers. It's the same no matter what. So, since my answer minus their answer is a constant, both of our answers are, well, they're either both wrong or they're both right. I really have a firm feeling that theirs is definitely right. They have a very powerful computer to calculate these things. So, my answer I would take to definitely be right. So there's a way that you can check them even if they don't look the same. So we have this one, we have sine to the -3/2 of x cosine cubed of x. So it's probably best, I think, well, some trial and error is not such a bad idea. I think what I'll try to do is break this up into cosine squared times cosine. The reason why I'll do that is because then I want to change cosine squared into 1 minus sine squared. And change this is a sine. Now I'm ready for my u. U equals sine of x du equals cosine of x dx. So this equals u to the negative 3/2 times 1 minus u squared du. So I'm all in terms of u right now. Let me go ahead and multiply the u to the negative 3/2 through. That'll be a u to the positive 1/2. The exponent here is 4/2 if you need a little help with arithmetic. And then when I integrate, I'm going to get x to the negative, or u to the negative 1/2. But when I divide by negative 1/2, it comes out to be a negative 2. And I'll take this to the 3/2. 2/3 u to the 3/2 plus c. And then let's go ahead and throw in, what was u again? U was sine of x. So we end up with negative 2 sine to the negative 1/2 of x minus 2/3 sine to the 3/2 x plus a constant. For example 7, consider this one. We're going to have sine of mx times cosine of nx dx. Now this one, rarely do students get this one because I have not actually done it in class, and it's a complicated, I don't know if you call it complicated, but there's a trick to it, I guess. And the trick looks like this. Remember this formula, cosine of alpha plus beta. No, I want to mix sine and cosine, so we'll instead use sine. And that equals sine of alpha cosine of beta plus sine of beta cosine of alpha. And then sine of alpha minus beta equals sine of alpha cosine of beta minus sine of beta cosine of alpha. And now what I'm going to do is add these two equations together. And I get sine of alpha plus beta plus sine alpha minus beta equals, notice what happens here. This part will disappear and you'll get 2 sine alpha cosine of beta. I can't use the double angle identity because alpha and beta may not be the same angle. But I do have this working for me. So if you look here, I can divide by 2, and I can get sine of alpha cosine of beta to equal 1/2 sine alpha plus beta plus 1/2 sine alpha minus beta. How does that apply to ours? Well, I'm going to think of alpha, mx will be my alpha, and nx will be my beta. So when I try to change sine mx times cosine nx, that's going to equal 1/2 sine of mx plus nx plus 1/2 sine of mx minus nx. I didn't say what m and n are, and I was assuming that m and n are both natural numbers. So with that in mind, let me do one more step with this. This will be 1/2 sine of m plus n x plus 1/2 sine m minus n x. I factored the x out of both of them. So let me have my integral back. So this is going to equal, I'll pull the 1/2 out front of the integral. So I have sine of m plus n x plus sine of m minus n x dx. And now they're easy to integrate. If you were to let a u be an m plus nx, then du would equal just m plus n dx, and then you would divide by m plus n. So you end up with 1/2, well, negative 1/2 cosine of m plus nx divided by m plus n. And then for the other one, we get plus, that's going to be minusing because the antiderivative is cosine, minus 1 over 2 times m minus n times cosine of m minus n x. And then we've got a plus c at the very end of all that. One thing I should have put here, there's a little bit of a problem, is if m equals n, then I can't do this. And if m equals n, then I wouldn't even bothered with this anyways. I would have had another method to use. So make sure we say that m does not equal n so that we don't have a chance for having a 0 in the denominator. So the ones are superfluous, so I'll get rid of them. For the next example, I have always found this particular integral to be quite annoying because it always seems like I forget what the trick is or something like that. But there's not a lot of trick to it. I can do secant squared x times secant of x dx. The idea is I'm going to use integration by parts. So I'm going to let u will equal secant of x. Then du will equal secant of x tangent of x dx. And then dv I'm going to let be secant squared of x times dx. Reason for that is because v is simply tangent of x. So let me get that stuff out of my way. This guy right here then, that integral equals uv, so I'll get the secant x tangent of x minus v du. So I'm going to get tangent times this stuff, and I'll end up with secant x tangent squared of x dx. All right, then I'm going to do an identity once again. This piece right here equals tangent is secant squared of x minus 1. Okay, I'll do one more step. Secant of x tangent of x minus, I'll multiply the secant through and get secant cubed x minus secant of x dx. Well, this is very nice because then I'll get secant of x tangent of x. I'm going to split this integral up. Now, we're trying to find this integral. Let me put it back over here. The original problem was secant cubed of x dx. So what I'm going to do is add this integral to the other side. So I get 2 secant cubed of x dx equals, so I got my secant of x tangent of x. But then right here I have left over, you're supposed to have memorized the antiderivative for that. It's the natural logarithm of the absolute value of secant of x plus tangent of x. And then at the very bottom here, I'll put a plus c. I'm not quite finished. A little bit too quick. I should divide both sides by 1/2 before I call this quits. And this last piece, c over 2 is still c. C, the constant sort of like sucks in all constants with it. So there's my answer. Well, I've done, it looks to me like I have a definite integral here. This is an easy one. I have tangent cubed of x secant squared of x dx. And from this you should see that secant squared is the derivative of tangent. So if I let u equal tangent, then I would simply have u cubed du. So that's exactly what I'm going to do. So this will give me then the integral. Now let me change my limits of integration. If I plug 0 in for x, tangent of 0 is 0. If I plug pi over 4 in for x, tangent of pi over 4 is 1. That way I don't have to put back the x's ever. I'm done with them now. So I get u cubed du, just like I said. This integral is so easy, I'm just going to leave it to you. You get 1/4. All right, for this one, I think I'm going to go the route of tangent. Remember, secant squared is the derivative of tangent, but this isn't quite secant squared. What you can do, though, if you don't mind, I'm going to change this to a 1/2 power. So I'll have tangent to the 1/2 of x secant squared of x times secant squared of x dx. And then what I'm going to do is use the identity for secant squared, which secant squared equals 1 plus tangent squared. Now I'm ready for my u substitution. So I can do u equals tangent of x, then du equals secant squared x dx. So all this stuff right here, this is the du. I'll sort of cordon this off. So then this will be u to the 1/2. This will be u squared plus 1. And then this is du. Now all I got to do is multiply out and then finish it off. U to the 1/2 times u to the 2 is u to the 5/2. And then I'll have plus u to the 1/2. Okay. U to the 5/2 will become u to the 7/2, become 2/7, u to the 7/2. And the other one will become 2/3, u to the 3/2, plus a constant. And I'm finally ready to put my u back. What was that? U was tangent. So I get 2/7 tangent to the 7/2 x plus 2/3 tangent to the 3/2 x. And then don't forget the plus the constant.